Hi, my name is Ethan Weiner, and today we will attempt to prove that 9 to the n minus 1 is divisible by 8 for all n greater than 0. As you'll see in a bit, the general intuition behind this proof is to first see if our statement is true at the lowest value of n we want to prove, which is n equals 1, and then see if knowing that the statement is true at some arbitrary value of n allows us to prove the statement for other values of n. However, in the proof, we'll actually do the statements the other way around. We will write our statement in terms of a predicate, p of n, just so that it's easier to refer to throughout the rest of the proof. We must first form our inductive hypothesis, which is an assumption that we'll make to help us guide through our proof. Let's assume that 9 to the n minus 1 is divisible by 8 for a particular value of n greater than 0. Let's call this value k and our statement p of k. Now, we should think about what we might be able to prove using this assumption, and a good place to start is just to see if we can prove the statement is true at the next value of k, which is k plus 1. So that we can better see what we're trying to prove, we'll actually go ahead and write out this statement. In order to show that p of k implies p of k plus 1, we must somehow relate the two statements. To make these statements easier to prove, we'll actually go ahead and convert them into an algebraic form, which will be easier to work with. So saying that 9 to the k minus 1 is divisible by 8 is roughly equivalent to saying that 9 to the k minus 1 equals 8a for some integer a by the definition of divisibility. And we can write something similar for 9 to the k plus 1. So our goal, in a sense, is to prove that the left side of the second equation, 9 to the k plus 1 minus 1, can be written as 8 times some integer, because that will help us prove that 9 to the k plus 1 minus 1 is divisible by 8. It doesn't matter what this integer is, we just got to find some integer. Now, the idea with the inductive step is to see if the first equation will help us prove what we need in the second equation by somehow relating them. By exponent properties, we can break up the 9 to the k plus 1 term into 9 to the k and 9 to the first. Now, it kind of looks like that in order to retrieve 9 to the k minus 1, we want to be able to somehow get rid of this 9 to the first. And here's where a bit of cleverness is helpful. When we break up the second term, negative 1, into negative 9 and 8, we can actually go ahead and factor out a 9. So now it is easy to see that we can use the equation we derive from p of k in our equation that we want to prove for p of k plus 1 by just plugging in 8a. Our final goal is to show that this second equation can be written as 8 times some integer, and if we proceed to factor out an 8, we get 8 times 9a plus 1. And we know that 9a plus 1 is an integer since a is an integer. And now we know that by the definition of divisibility, 9 to the k plus 1 minus 1 is also just divisible by 8, and we have proved that p of k implies p of k plus 1. Since k is just an arbitrary number, our singular implication here actually represents what I'll call a chain of implications. We know that p of 1 implies p of 2, but p of 2 must also imply p of 3, and so on. But this is all that we've proved, that one statement implies the next. We haven't actually shown that any of these statements themselves are true, and we want to show that all of these statements are true. So, how can we miraculously do this? Well, if we just show that the leftmost statement, p of 1, is true, the rest of the statements must also be true. This is just the nature of implications. Some people refer to this as the domino effect, because if we know that one statement is true, then it metaphorically knocks over the next domino, which knocks over the following domino, and so on. So let's go ahead and actually prove p of 1. At n equals 1, our statement becomes 9 to the first minus 1 is divisible by 8, which, by the definition of divisibility again, is true if and only if 9 to the first minus 1 equals 8a for some integer a. And it's easy to see that 9 to the first minus 1 equals 8 times 1, and 1 is an integer. So we've shown that p of 1 is true, and by induction, we know that p of 2 is true, and so on. So p of n is true for all n greater than 0. So to summarize, we assume that 9 to the n minus 1 is divisible by 8 at a particular n equal k, and we saw that using this assumption, it is also divisible by 8 at k plus 1. Then we show that it is divisible by 8 for the lowest n in our range, which is n equal 1. And these two pieces together create this sort of domino effect, rendering the statement true for all n greater than 0.